Good morning. So this is Dr. Umesha from Vidyavardhaka College of Engineering. Today I'm going to talk on solid mechanics. That is flexural and shear stresses we are going to talk today. So so I will solve mainly problems which has come in most of the previous papers, previous gate papers. So today we'll talk on flexure and shear stresses. So bending stresses. So we'll take the problems only. So all the theory you might have already learned. So I will not repeat any theory. So directly I will take the problems which is very complicated and how to solve each of them. I will explain in this session. So take a problem: a cantilever beam with the uniform flexural rigidity, EI is equal to 100 into 10 to the power of 6 Newton meter square is loaded with a concentrated force at its free end. The area of a bending moment diagram corresponding to the full length of the beam is 10,000 Newton meter square. The magnitude of the slope of the beam at its free end is dash microradians, round up to the nearest integer. So these are the different options they are given. So we'll see that one. This is a cantilever beam. It is subjected to a concentric at the free end. So because of that one, this is the bending moment diagram. So we know that one, that is the change of slope between any 2 points on the elastic curve equals to the area of M by EI diagram between these 2 points. So that is the main logic you have to remember here. So what are the angle? So theta B minus theta A. So is equal to, that is the slope, is equal to area of EI diagram. So M by EI diagram. So theta A is a fixed end. So there will be no theta A. So theta B is equal to A. They have given already the area of M by EI diagram. So that is area 10,000 Newton meter square divided by EI. Also they are given EI is equal to, so 200 into 10 to the power of 6. So that is equal to, so we will be getting 0.5 into 10 to the power of minus 4 radians. That can be written as 50 micron radians. So this is option they given B. So EI, it should be 200 here. EI, the fracture rigidity, EI is equal to 200 into 10 to the power of 6 Newton meter square. By mistake it has come here, so we have taken 200 only. So 1 by 2 is equal to 0.5 is coming. So you take the option, that one, you will be getting 10 to the power of minus 4 radians. That can be written as 50 micron radians. So option B is the correct one. So we'll take next problem. So cantilever beam of length L, flexuridity EI, is subjected to an end moment M, as shown in the figure. The deflection of the beam at x is equal to L by 2 is. So this is the beam they given, the moment acting at the free end. So they are asking the what is the deflection of the beam at x is equal to L by 2. So these are the different options they given. So we'll see how to calculate at deflection at L by 2. So this is the moment acting. So moment diagram. So it can be written as this one. That is the whole beam will be having the M moment. So they want to know what is the deflection of the beam at x is equal to L by 2. So if you take YC minus YA is equal to AX bar divided by EI. So YC minus YA is equal to 1 by EI is equal to minus ML. So actually what you are doing here, the area of M by EI diagram into the distance. So centroidal distance from that one. So that is, we know that one M into L, that is M is the moment, into L by 2 is the length of this one. So at a distance L by 4, that is the distance here. So AX bar divided by EI. So YC is equal to ML square by 8 EI. So that will be option C. C option is the correct answer. So what you have done here, we have drawn the moment due to moment diagram due to the moment acting at the free end. So this is the moment diagram. So once if you become the moment diagram in the M by EI diagram, it will become fixed end, it will be free end. So we wanted to calculate here. So YC is equal to AX bar divided by EI. So that is the logic here. We'll take another problem. A overhanging beam PQR is subjected to uniformly distributed load 200 kilonewton per meter as shown in the figure. The bending stress developed in the beam is dash MPa. So they ask us to round up the response. This is the overhanging beam, overhanging, that is PQR. So it will be loaded with the UDL, that is a 20 kilonewton per meter. So this is the dimensions they are given, that is a 2000 millimeter, and this is 1000 millimeter. This is cross section of that one. So these are the different options. So we will see how to calculate the maximum bending moment. So we have to calculate the maximum moment due to this overhanging beam. So this is the UDL. UDL can be converted. This will be half of this 2 meter. So 20 kilonewton per meter into 2 meter will be 40 kilonewton will be acting at the center. And here overhanging, so 20 into 20 kilonewton, that will be acting at this point, 20 kilonewton, it will be acting here. So the reaction can be calculated by knowing that one. So we'll be getting the reaction, taking the moment at this one, calculate the reaction RA, RB, that is RA is equal to 15 kilonewton and RB is equal to 45 kilonewton will get. So once if you know that one, you can write the shear force diagram. This is the shear force diagram. So also we know that one where the shear force is 0, we will get the maximum moment. So we have got 2 points, one here and one here. So we have to calculate the moment at this point and this point. So we'll see some moment here at MD. So you can calculate the moment at MD is equal to 5.625. It will be coming a positive. So what you have to do, you take the here and 1.15 kilometer into 1.1 meter. So you'll get the moment at this point. And MB, so this is the cantilever portion you can take, that is uh, 20 into 1 meter divided by half of that one, that is a 10 kilonewton meter will be coming. So this will be 20 kilonewton. So okay, so you'll be getting, so from the shear force diagram, this is the point you can get the point x and 2 minus x. So we'll be getting the maximum moment MB is equal to, that is the maximum compared to MD and MB, we'll be getting MB is the maximum. So you take that maximum stress. So what you have to do, the maximum stress for that one will be 10 kilonewton meter will be getting. So stress is equal to, what is that? Stress is equal to M by Z. So we'll be knowing from the moment diagram, that is Fy is equal to M by Fy is equal to M by Z we have. So you have the formula. So from that one you can calculate. So from the formula you can hear. So M by Z is equal to BD square by 6 will be there. So answer will be, you'll be getting a 250. Answer is B as answer the correct one. So we'll take the next problem. Consider an elastic beam of length L is equal to 10 pi meter with the square cross section of side A is equal to 5 millimeter and Young's modulus E is equal to 200 GPa. This straight beam was bent in such a way that the two ends meet to form a circle of mean radius R. Assuming Euler-Bernoulli's beam theory is applicable to this bending problem, the maximum tensile bending stress in the bent beam is dash MPa. So these are the different options. So we'll see that one. This is the length 10 L is equal to 10 pi. So they will be bent in the form and join at this point. So we'll be having, so what is the length? Length of the wire is equal to, so that is equal to L is equal to pi into D. So that is equal to 2 pi R. So total length given 10 pi is equal to 2 pi R. So R is equal to 5 meter. We will be getting some R radius. So once if you know the radius, we from the bending equation, M by I is equal to F by Y is equal to E by R. So we are interested to know F by Y is equal to E by R. So we know the Young's modulus they given, R we have calculated. So we wanted to calculate the what is the tensile stress that is at the top. So yeah, maximum is equal to Y maximum into E by R. So E they given, Y maximum what is that? Here they given 5 mm. So we have to calculate 2.5 into 10 to the 200 into 10 to the power of 3 divided by R. That is converted into millimeter. So we'll be getting 100 MPa. So answer will be A is the correct answer. So we'll take next problem. So cantilever beam of length 2 meter with the square section of side 0.1 meter is loaded vertically at the free end. The vertical displacement at the free end is 5 mm. The beam is made up of steel with Young's modulus 2 into 10 to the power of 11 Newton per meter square. The maximum bending stress at the fixed end of the cantilever is the given the option. So they given different options here. So we want to calculate this is the cantilever beam loaded with at the end. So this is a 2 meter length they given and the side zero point 0.1 by zero point 0.1 is the square section. So deflection of the cantilever beam will be delta is equal to PL square by 3EI. So that is equal to deflection they are given. So that is a 5 mm, that is a 5 into 10 to the power of minus 3, that is equal to PL square. That is converted into all the things into meter. So you are converted here meter. 2 into P into L cube, that is 2 cube divided by 3 into 2. 2 into 10 to the power of 11 is the E value into 0.1 to the power of 4, that is I. I is equal to, that is BD cube by 12. So B and D are both are same. That's why 0.1 whole to the power of 5 by 12. So P is equal to, so you'll be getting the value. So moment will be calculated at the end is equal to 3125 into 2. So that is the option. So Newton meter will be getting. So M by I is equal to F by Y, or stress by Y is equal to E by R. So maximum stress is equal to M by Z. So we'll be calculating 6,250 divided by that Z square. BD square by 6. So we'll be getting 37.5 uh, Newton per millimeter square. So that will be MPa. So option B is the correct answer. So what you have done here, only thing you should know the deflection for the cantilever beam loaded with a concentrated point, and the equation formula for bending equation, M by E is equal to F by Y, or stress by Y is equal to E by R. So maximum stress will be calculated. It will be at the top portion will be there. Okay. So then we'll take another problem. So a 450 long plain concrete prism is subjected to the concentrated vertical load as shown in the figure. So cross section of the prism is given as 150 by 150 Considering the linear stress distribution across the cross section, the modulus of rupture, so MPa is given what? So they given the different options. So we should know that one. This is the given in the formula. So this is the length. So 450 is the length of the beam. So what you have to calculate? You have to calculate the moment at Q. So that is 11.25. That is the reaction you can calculate because it's a uniform 150, 150, 150 will be there. So reaction is equal to 11.25 kilonewton. So into the distance 150, you will be getting the bending moment at MQ. So stress by distance y is equal to MQ divided by I. Y is equal to, we know that 150 by 150, that is 150 by 2, that is 75 I is equal to 150 to the power of 4 divided by 12, that is the B to the power of 4. So you can calculate the maximum stress. So you calculate the bending moment you have calculated, and we know the Y value divided by I. So you'll be getting 3 MPa. So answer D is the correct answer. So what you have done here, you will calculate the bending moment, and the maximum bending moment, it will occur at the point either Q or R. So we calculate using the bending equation. We have calculated the maximum stress. So we will take another problem. A homogeneous simply supported prismatic beam of width B and depth D and span L is subjected to a concentrated load of magnitude P. The load can be placed anywhere along the span of the beam. The maximum flexural stress developed in the beam is. So this is the different options they are given. So what they are telling is a simply supported prismatic beam they are given. So what they're doing here of length. So when it will be happen, the maximum bending moment. So when the constant load is placed at the mid span, so maximum bending moment will occur. So they want to test where for you. So that's why they're telling the maximum bending moment will occur at the mid span. So once if you know the maximum bending moment, so bending equation is F by Y is equal to M by I. So F can calculate M by I is equal to 1 to Y. So maximum bending moment for the simply supported beam with of a span length L. So you'll be getting PL by 4, that is the maximum bending moment. So Y is equal to D by 2, I is equal to BD by 12. So substituting all the things, you will be getting 3PL divided by 2 BD square. So option C is D is the correct answer. Okay. So what you have done here, only we should know where it will occur the maximum moment in the simply supported beam. So for the constant load, if we give UDL, it will be different. That have to calculate accordingly that maximum bending moment. So okay, they will take another problem. A simply supported beam of length 3L is subjected to the loading as shown in the figure. So it is given P is equal to 1, L is equal to 1, and Young's model is equal to E is equal to 200 GPa. The cross section is a square with the dimensions of 10 by 10 mm. So bending stress in Pascal at the at the point A. At the point A, they wanted to calculate at the midpoint located at the top surface of the beam at a distance 1.5 meter from the left end. So these are the different options they're given. So now they're given one upward load and one downward load, and we have to calculate the reactions of R1 and R2. So that is easy. You can calculate the reactions. R1 R2 is equal to P by 3. R2 is equal to P by 3 upward, and R1 is equal to P by 3. It will be downward. Negative is it is downward. Once if you know the reactions, we can calculate the moment at A at a distance at 1.5 meter from here. So R1 into 1.5, either you can take left side or right side into 1.5 plus P into zero point 0.5 L. So we'll be calculating the moment. Moment will be getting 0. So once if the moment is 0, from if you substitute in the bending equation, we will be getting the bending stress is equal to 0. So option C is the correct one. So very simple only. You have to analyze that one, and so no need to calculate anything. See, all the things will be coming. You will be getting the moment 0. Once if you moment 0, the bending stress is equal to 0. So that is the thing. Then we will take another problem. A simply supported beam of span 6 meter and 75 diameter carries uniformly distributed load of 1.5 kilonewton per meter. What is the maximum value of the bending stress? So what they're given the different options here. So what they're given here. So we bend from the bending equation is equal to sigma by y is equal to m by I. Sigma you can calculate m by I is equal to into y. Maximum moment here they're given uniformly distributed load 1.5 kilonewton per meter. So WL square by 8 is the maximum moment. So once if we calculate the maximum moment and y is equal to d by 2, that is they're asking at the upper tension side. So 75 is the diameter, 75 by 2 is the y, and I is equal to, for the circular one, b pi d to the power 4 by 64 you'll be getting. Once if you calculate all the things, and if you substitute in the bending equation, that is sigma is equal to 162.97 MPa will get. So option A is the correct one. So differently they're asking that one, so you can see. So here the massless beam has a section with a width of 300 mm and height of 100 mm. The maximum moment of bending stress is given by. So what is the maximum magnitude of bending stress? So this is the different options they given. So we'll see that one here they given the half the portion they given the UDL. So that is 3000 Newton per meter they given. So we have to calculate what is the maximum bending moment where it will occur. So it is very important. The maximum moment will occur. So equation for the bending moment you can write. So once if you calculate the reactions, you can calculate the reactions for this UDL. So once if you know that 1500 will be getting here and 4500 here. So that is Pascal. So once if you know that one, maximum bending moment equal to 1500 into x at a distance x. So 3000 by 2, that is WL square by 2. That is the distance from here. So we have to calculate the distance from this one. So if you distribute, if you take the different, that is first derivative and equal to 0, we will be getting the x is equal to 2.5 meter. That is 2 meter here and 2.5 at the point. So once if we know the x value, you can substitute here and we get the maximum bending moment. Once if we get the maximum moment, bending stress is equal to m by z. That is very simple. Only thing we have to calculate the maximum bending moment due to that partial ODL. So m by z, that is z is equal to bd square by 6 will be there. So 6 maximum moment you have substituted. So BD square will be substitute all the things you will be getting. Z is equal to BD square by 2. That is will be in the coming 6 will be coming here. So BD square. So that will be converted into meter. So we'll be getting 67.5 into 10 to the power 6 Newton per meter square. So that is equal to 67.5 MPa. They want answer in MPa. So B answer is the correct answer. So only thing, important thing here, how to calculate the maximum moment. So for that one, you have to calculate reactions and write the equation for bending moment in terms of x. Then once if you differentiate that one, you will be getting the x value and substitute here, you will get the maximum bending moment. That is the first one. Then you will go for the shear stresses. The transverse shear stress acting in a beam of a rectangular cross section subjected to transverse shear load is, so they are given different options. Variable with the maximum at the bottom of the beam, variable with the maximum at the top of the beam, uniform variable with the maximum at the neutral axis. So we know that one any rectangle section, the shear force will be varying like this. So it will be 0 at the top and bottom, and it will be maximum. It will be variable. So at the neutral axis, it is neutral axis. It will be maximum. So variable with the maximum at the neutral axis. Answer D is the correct answer. So we'll go next to shear stress. Shear stress at the neutral axis in a beam triangular section with a base of 40 mm and height of 20 mm subjected to a shear force 3 kilonewton is. So they want to know what is the shear force. So this is the different options they given. This is a triangle they given, that is for 40 mm base width and height is 20. So we know that one the neutral axis will be at one third of the height from the bottom or two third from the top. So they want to know, we are interested to know at the top only. That is a two-third means 40 by 3. So once if we know that one, we have to calculate what is the shear stress, that is force S A y bar divided by I into B. So width at the distance 40 by 3 mm from the top. So that you can calculate from the similar triangles. So width, what is the width? So we calculate here 80 by 3 mm. So once if you know width, and we have to calculate the area. So that is a shear force they given here. Shear force is 3 kilonewton, and the area of this portion. So half into base into height. So base you have calculated here, height also 40 by 3. That is the area of that triangular portion, and y bar from here, y bar of that one, that is one third of 40 by 3. So that will be there divided by I, moment of inertia of the triangle section, that is BDQ by 36, it will be there, into B is equal to what is the width at this point, that is 80 by 3. Once you simplify, we'll get the stress 10 MPa, that is answer C. So very simple only. I think we should be calculating very fast. So we will take another example of shear stress. A symmetrical I section, that is with the width of a flange is equal to 5 mm, thickness of the flange is equal to 10 mm, depth of the web is equal to 100 mm, and thickness of the web is equal to 10 mm. Of steel is subjected to shear force of 100 kilonewton. Find the magnitude and shear stress in MPa in the web of at the junction with the top flange. So these are the different options they're given. So this is the one what they're given here. That is a 50 by 10. That is 100 by 10 will be there. So they are interested to know what is the shear force at the junction point of the top flange. So I moment of inertia can calculate for this portion, that is equal to 50. That is a moment of inertia of the I section can be written as this one. So once if you know the moment of inertia, that shear force they given, that is 100 kilonewton, and the area of this portion 50 into 10 is the area, and this is the centroid distance from here, that is 55 mm. So divided by moment of inertia into B. B will be there at the this portion only. So 10 mm will be there. So once if we simplify that one, we'll be getting 71.12. That is the answer. B is the correct one. So we'll go next one. Shear stress. I section of a beam is formed by gluing word flank as shown in the figure below. If this beam transmits a constant vertical shear force of 3000 Newton, the glue at any of the four joint will be subjected to shear force of. So this is the figure they given. So this is the one here, and another planks will be glued at these points, 4 points. So this is a 50 by 200. This is the 50. This is 200. 50. This is 75. This is 50. This is 200. So when they given the different options, so to calculate that one, this is the one. If you take portion of that one, that is 75 into 50. So considering the shaded area of ABCD of the flank, shear flow it can be written as V cube divided by I. So Q is equal to A into Y bar. Q is equal to A is equal to area of this one 75 into 50, and Y bar is equal to from the centroid of this one. So half of this one 100 plus this is 25, 125. So you'll be getting the Q value. Then moment of inertia of the I section can be calculated for this one. Then Q is equal to V. We can calculate already they given 3000 Newton, and Q value we calculated divided by moment of inertia. We'll be getting approximately 4 Newton per millimeter. So that option B is the correct one. So we'll take another problem of shear stress. Consider a simply supported beam of length 50 h with a rectangular cross section of depth h and width 2 h. The beam carries a vertical point load P at its midpoint. The ratio of maximum shear stress to the maximum bending stress in the beam is. So they want to know uh, ratio of the maximum shear stress to the bending shear stress. So they ask us to calculate both. So here the shear stress equal to VQ by IB will be there. So that is the maximum shear stress will be 3 by 2 shear force divided by area. So that is the maximum shear stress. We can calculate P maximum is equal to, you'll be getting P by 2 because if it is simply supported beam only, vertical load P acting at the midpoint. So that will be shear force equal to P by 2. So this is, so if you simplify that one, area. So 3 P equal to P h square. So 0.75 into P maximum divided by h square. 0.75 h square you can substitute here, and h square. So P is equal to P by 2 will be there. So you'll be getting in this form. So this is the one tau maximum. So we calculate similarly sigma y by y is equal to m by I. So we have to calculate the maximum bending moment PL by 4 will be there, and z is equal to ph square by 6 it will be there. So calculate the sigma max. So m max by z. So we'll be getting 37.5 ph square. Here 0.375 ph square will be there. So the ratio will be getting 0.01. So answer D is the correct one. So we'll go next problem. Buckling of columns. So we'll see that how buckling of columns. Cross section of a column consists of we'll see only problems. Two steel strips, each thickness of T and width B is shown in the figure below. The critical load of the column with the perfect bond and without bond between the strips are P and P0 respectively. The ratio of P to P0 is. So this is the one they are given two planks of a thickness T and breadth B. They are one time they are without bond and without bond, with bond and without bond. So with the bond means it will be acting as together. So two T will be their thickness. There is a different options. So we know that one critical load of the proportional to the moment of inertia. So pi square. So we know that one. What is the formula for the critical value? That is the pi square EI by L square will be there. So it will be proportional to the moment of inertia of irrespective of end condition and the of the column. So this is a formula. When the steel strips are perfectly bonded, then the thickness will be 2T. So moment of inertia is equal to B thickness cube divided by 12, it will be there. So when the strips are not bonded, then two times. So you can take it two times thickness of T. So that will you will be getting the moment of inertia of that one. So I by I zero. So if you take that will be proportional of the P critical of I, that is combined one and without combined one. So we'll be getting the ratio of 4. So as B, so what you have done here, so simply you have taken the critical load is proportional to the moment of inertia. So once if it is a bonded, it will act together. So thickness will become 2T, and here the only T will be there, and two times that is the ratio you have taken. So because of that one, you'll be getting the ratio of that one is equal to 4. So we'll take another problem. A steel column pinned at both points has a buckling load of 200 kilonewton. If the column is restrained against the lateral movement and its mid height, its buckling load will be. So that they given different options. We'll see that on how to calculate. When both ends are hinged, the buckling load is given by pi square E by L square. That they given 200 kilonewton. So when the lateral movement of the mid height is not allowed, then the buckling load is equal to that is held in position. So what will happen that L1 is equal to L by 2 will become so pi square EI by L1 square. So if you substitute that one is equal to become to 4 pi square by EI by L square. That's equal to 2 into 4 into 200. So 800 kilonewton. That is option D is the correct one. So we'll see another problem. So a long structural column of length L with both the ends hinged is acting upon a axial compressive load P. The governing differential equation of the bending is given by, so we know that one EI d square y by dx is equal to minus Py. That is the equation. When y is the structural lateral deflection and EI is the flexure rigidity, the first critical load on column responsible for the buckling load will be. So we simply they're confusing all the things. So we know that one if it is both and fixed, we'll be knowing the buckling load will be pi square E by L square. So option A is the correct. So they given description all the things. So no need to worry. It will be only. So we should know what is the boundary condition. So they given both and hinged, and all the things they are given. What the flexure rigidity equations, everything they are given. They'll confuse that one. So option E A is the correct one. So we'll take another example. If a buckling load P is equal to P critical of the column AB as shown in the figure, okay, approaches as KT, that is the stiffness at the point it could approaches infinity, becomes alpha pi square E by L square, where alpha is equal to. So they want to know what is the value of alpha. So it is depends upon the your fixity condition. So here once if you become fixity, it will be fixed condition will be there. So hence the option D. So fixed condition here it will not be allowed. So fixed will be 4 times L by 2 will be there. So pi square E by L square, that is L is equal to L by 2 it will become. So for the fixed column, so it will become 4. Answer will be the D. So we'll take another example. Consider two axially loaded column, namely 1 and 2, made of linear elastic material with the Young's modulus 2 into 10 to the power 5 MPa, square cross section with the side 10 mm and length 1 meter. For column 1, one end is fixed and another end free, and column 2, one end is fixed and other end is pinned. Based on the Euler theory, the ratio of the buckling load of column 2 to the buckling load of column 1 is. So they want to know column 2 to column 1. Column 2 is the fixed one hand and another pin hand. So you want to know what is the ratio of that one. So once in the column 1, it's fixed and free here, and column 2, fixed and hinged here. So we know that what is the effective length. So if it is free end, it will be L is equal to 2L. If it is hinged at the top and bottom is fixed, it will be L by root 2. So if you substitute all the things, you will be getting the ratio of that one. So you will be getting 8. So answer B is the correct answer. So all the things they given description, you have to go through fast and see that column 1, column 2, what are the boundary conditions, what is the, and then the effective length. Once if you substitute that one, it will be, all the things will get cancelled and you will be getting the constant ratio, that is 8. So we will take another example. In a system, two connected rigid bars, A and AC and BC are identical length, uh, L with the pin support at A and B. The bar are interconnected at C by a frictionless hinge. The rotation of the hinge is restrained by the rotational spring of stiffness K. The system initially assumes a straight line configuration ACB. Assume both the bars are weightless and the rotation at the support A and B due to the transverse load applied at the C is. So they're given different options. So this is the one. So they're given AC and BC as identical. So we want to know rotation they're given and stiffness they're given at this point and hinge point they're given. So this is the theta and theta. Because of this one, it will become 2 theta. So what is the work done? So we know that the deflection under the load is equal to P is equal to theta into L. So that is equal to, we'll be getting the work done by the force P is equal to whatever P is acting here, half into P theta L, and strain energy stored in the spring is equal to, so they given stiffness, they already given stiffness into 2 theta into 2 theta. So equating the work done is equal to strain energy, we'll be equating that one, and we can calculate the theta. So that's what they want to know, what is the rotation at the supports A and B due to the transverse load P at C. So equation option first one will be the correct one, PL by 4K. So we'll take another example. So two steel columns P of length L is equal to L and yield strength 250, and second one Q is equal to length 2L and yield strength 500, have the same cross section and end conditions. The ratio of buckling load of P2 to that of Q is equal to, so they want to know two columns, that is yeah, mainly here pi square A by L effective you have to take. P is equal to here, because of conditions you can see here, they given L length and 250. So you can substitute all the things, you will be getting PP divided by PQ is equal to 4 actually. You have to substitute all the things. This L effective is equal to L is here, and here, so we have the 500 here. Substitute all the things, you will be getting PP to PPQ is equal to 4. So option D is the correct one. So take another example. The sketch shows the column with a pin at the base and the rollers at the top, subjected to the axial force P and a moment M at the midpoint. So the reaction R. So what are the reactions will be there? So once if you calculate here, so here hinge will be there, we will be having the horizontal force. So if you take the reaction at this point, so one vertical force will be there and horizontal force equivalent to M by H. So you can H plus 2, H plus 2, so M by H. So option C is the correct. So you can calculate this one, take the horizontal force here and take the moment here, and we will be getting moment divided by H reaction. So that the reaction will be coming here also. So option C is the correct one. That means vertical force will be there and the horizontal force equal to M by H. So we'll take another example. The ratio of a theoretical critical buckling load for a column with a fixed point that to another that of the same dimension and material but pinned. So that can be written as very easy. So answer D is the correct answer. So we'll take another example. The effective length of a column L fixed against rotation and translation at one end and free at the other end. So that will be D is the correct answer. So mainly that effective L effective length is the 1. So you take another example, rigid bar GH of length L, it is supported by a hinge and the spring stiffness K as shown in the figure below. The buckling load P critical of the bar is given by, this is the one they are given. So see the load is acting here and the spring they are given here. So that can be written as here. So only thing of what you have to, the load will be deflected by delta. So that stiffness force is equal to stiffness into delta it will be there. So equating that one, P critical into delta is equal to F into L. So we'll be getting P critical equal to KL. So that is equal to C answer the correct. We'll take another example. The stress problem. So here is shown in the figure as four members of length and rigidity as shown in the figure. So what you have to do, so all the things will be there. They want to know which is the smallest value of P at which any of the truss members will buckle. So mainly main force will be there at the this point will be. So will be since the buckling will happen due to compression only and it occurs in the diagonal member only. So once if you know that one, you can calculate the diagonal member forces and calculate all the value, and you will be getting 2 pi square by E by L square. So that will be in the here. Option C is the correct one. So we'll take another example. Consider a steel Young's modulus E is equal to 200 GPa, column hinged at both the sides, and its height is equal to 1 meter and cross section is equal to 10 by 20 mm. The lowest critical section. So here nothing else. Only thing pi square E by L E square. So direct formula here. So you can substitute. Answer A is the correct one. So we'll take another example. So a column has the rectangular cross section 10 by 20 of length 1 meter. What is the slenderness ratio? So only thing you should know the slenderness ratio. Slenderness ratio is equal to that is LQ divided by R minimum. So you have to calculate the R minimum. R minimum is equal to I minimum divided by A. So which is the giving the minimum moment of inertia that you have to divide by A. So slenderness you can calculate. So 346 is the correct answer. So we'll take another example. The rod PQ of length L and flexure rigidity E is hinged at both ends. What is the force expected to buckle? So this is the one. So you have to see here, different options are there. So reaction, calculate the reactions. What is the value in the force in the member? That is we're calculating. Considering the buckling equal to R is equal to P, R is equal to greater than P theta. So all the things you substitute equal to pi square E by I minimum you have to take. LE is equal to effective length. All the things you do here, alpha is equal to, it will become 1. And hence that value C is the correct one. So we'll take another example. What is the equation? So this is easy only. So fix it both ends. So we'll take another example. Column of height rectangular cross section A by 2A and a buckling load cross section change to 0.5A into 3A and height change to 1.5. What is the design? So we should apply here only thing the cross section they given, the cross section they given, the length they given. So load if you apply that one, we'll be getting the ratio of that one. What is the load? P by 12 will be getting if you simplify all the things. Okay. So answer A. So we'll take another example. A steel column pinned at both ends. Buckling load is equal to 200 kN. Column restrained against lateral movement at the mid height. So different options. Option will be 800 will be correct answer. So we'll take another example. Initially stress-free massless elastic beam of length cross section of diameter is very less is held two walls as shown in the figure and Young's model is given value the beam slowly uniformly heated the temperature. Here the temperature problem also given. This is the length. So it is proportional to what they're asking. So here mainly the temperature stresses you calculate. So once if we know calculate and we will be simplifying that one, we will be getting the delta T is proportional to D square, the diameter of the bar. So B is the, so you can see here all the things we know already know the temperature stresses and pi square E by the is a buckling load. So equating that is will be greater than that one. So proportional to that one. So shear center. So mainly what is the shear center you'll be knowing. So here this is the definition. This is the definition of shear center and answer C is the correct one. And this is the equation through Is it right? So this is the one you want to know whether it's a bending or a torsion. This is the torsion one. And the shear center, what is the shear center for the this one? So it will be here. It will be knowing that one. So that no twisting means that will be coming. E is equal to P is the correct answer. So that is the one. So shear center, another problem. If you take that one, this is the one. So we know that we know that one, that the shear center for a T section it will be here, and if it's the cross section it will be here. So once if you know that one, it is the point here. So the coordinates have to see. So this is the point A is the correct one. So thank you. Will if you have any doubt, you can contact me or you can mail to me. Thank you very much. So I have a good exam. Best of luck. I think